A cylinder of radius r and length L is lying on the x-axis as shown in the picture, and it has a variable resistivity that depends on x. We'd like to calculate the total resistance of this cylinder. If the cylinder had constant resistivity, then we could use this formula to calculate the resistance. So resistance is equal to resistivity times length L divided by the cross-sectional area A. So this would be valid for a cylinder of constant resistivity. But because the cylinder has variable resistivity, we can't use this for, we're going to use it, but we're going to have to imagine dividing our cylinder into slices along the x-axis and calculate or find an expression for the resistance of each slice using this formula, and then integrate over those slices. In other words, integrate along the x-axis. So then here's such a slice of thickness dx as shown in the picture. So that's like the length of my slice. And the cross-sectional area is constant along the cylinder, right? So that doesn't change. The cross-sectional area is going to be equal to pi r squared. So let's come up with an expression for the resistance of such an individual slice or unit element, and then we're going to integrate over those resistances. So the resistance of such an individual unit element is going to be dr, and we will integrate over dr basically. So here's my starting point. Total resistance R is equal to the sum of the resistance of each unit element, which is dr. So we're integrating over dr. Now in the next line, let's express dr using the resistivity formula. So I have substituted the expression from the resistivity formula. The resistance of such unit element is going to be equal to resistivity as a function of x times dx, that's the length of the unit element of the slice, divided by the cross-sectional area. In the next line, I'm going to substitute the formula for resistivity. Also, cross-sectional area is a circular area, so that's pi r squared. And here's my integral resistivity times dx divided by pi r squared. I can also set the lower and upper bounds of my integral. X runs from 0 to capital L. In the next step, I'm going to pull the constants outside of the integral sign. I'm referring to the pi r squared in the denominator. I will also take this integral. It's just a polynomial with two terms, so fairly simple. The integral of a is a times x. The integral of b, x squared, is equal to b x cubed divided by 3. And this is what we get when we evaluate our integral at the upper and lower bounds. Now, can we go ahead and plug in the numerical values? Unfortunately, not yet, because to complicate things further, we are not given the values of A and B. Instead, we are given the resistivity values at either end of the cylinder. So the resistivity value on the left-hand side, on the left end of the cylinder, and the resistivity value on the right end of the cylinder are given. So we're going to use those values to calculate A and B first, and then we can go back to the resistance formula or the result for that we got for resistance and plug in the numbers. The value of the resistivity on the left end of the cylinder is given as 1.85 times 10 to the negative 8 ohm meter. Now, when we plug in x equals 0 in the resistivity formula, we just get A, right? Because the second term is plus bx squared. That term goes away when x equals 0. So then A is equal to 1.85 times 10 to the negative 8 ohm meters. The resistivity at the right end, on the other hand, is equal to 9.55 times 10 to the negative 8 ohm meters. And that corresponds to x equals capital L. So A plus BL squared is equal to 9.55 times 10 to the negative 8 ohm meters. We rearrange our equation to isolate B and substitute the numerical values for A and capital L. We get B equals 2.37 times 10 to the negative 8 ohm per meter. Now note the unit change because B is ohm meter divided by meter squared, so the unit for B is ohm per meter. Now let's go ahead and substitute the numerical values in the expression for resistance and calculate the resistance of this cylinder. And after some tedious numerical calculation, here's what we get. Resistance is equal to 1.76 times 10 to negative 4 ohm. Note that in the formula above, in my final results above, I factored out one of the capital L's to make it look slightly simpler, and then plugged in the values. Next, we'd like to calculate the electric field magnitude at the midpoint of the cylinder if it carries an electric current of 1.20 amps. For this calculation, let's use the defining formula for resistivity, which is electric field magnitude divided by the current density. And current density J, that's electric current divided by the cross-sectional area. So in the next line, I'm going to substitute I divided by pi r squared for J. And here's what I get when I do that. Next, let's isolate the electric field magnitude and substitute the numerical values. Here I have isolated E. I'm also using the formula for resistivity, A plus BX squared. And I'm substituting L over 2 for X because we're looking for the electric field at the midpoint of the cylinder. So where X equals capital L divided by 2. And with the numerical value substituted, we get electric field magnitude equals 1.00 times 10 to negative 4 volts per meter. Next, we cut the cylinder from the middle and calculate the resistance of each half. The half on the left hand side is R1 and the half on the right hand side is R2. Let's calculate each resistance value. We are going to use our result from part A, so the same integral. We don't need to redo the integral. The only thing that changes is the integral limits for each half. So for the left hand side half R1, X runs from 0 to L over 2. And for the other half, the right hand side one, X runs from L over 2 to L. Here's R1. Let's evaluate it at the given integral limits from 0 to L over 2. Here's what we get for R1 after evaluating our integral. Now let's calculate R2. Same integral with different integral limits. This one runs from L over 2 to L. Here's what we get when we evaluate it at the given limits. This could be further simplified by combining the like terms. And here's what we get after the simplification. I'm not going to calculate the numerical value. You can go ahead and do that. Now we expect R1 to be less than R2 because resistivity increases with X.